All right, welcome back. This is part 2. We're starting with chapter 4, which you'll see has some math, but it's not too bad. If you did okay in high school physics, high school calculus, you'd probably be okay. But the key thing here is that we're defining a thing called a ray, which is just a point and a vector, a point and a direction. And it represents all the points in space that are along a line that you can get to by starting at point A and moving in the direction B. And they use this parameter t to mean how far you move. So if t is 0, you're at point A. If t is 1, you're moving along the ray a little bit and then further and further. They put the ray in its own file. I'm not going to bother with that. I'm just going to put it right here. But basically, it just has an origin, which is a point, and a direction, which is a vec. Point 3 is just an alias for vec3, same as color. Again, they use the same type for colors, points, and vecs. You could argue it would be better to make them 3 separate types, but I'm just going to follow what the book does. It is kind of convenient in some ways. And of course, this is unused because we haven't gotten to the code yet that constructs it. But that happens a lot in these type of tutorials because you'll write something that you're about to use, but you're not using it yet. And so I'm going to go ahead and suppress that warning. Great. I'm not going to bother with the constructor. It only has 2 fields, so we'll just construct it directly when we need one. And I'm not going to bother with these functions because they're just simple getters. But I will add this at function. Which returns a point 3. Orig or self.orig plus t times self.dir. And t is, of course, the parameter I forgot to put in. Great. So now we're going to send rays into the scene. So basically just think of a ray where its origin is the origin, where the camera is, and its direction is pointing out towards whichever pixel we're currently calculating. And then we'll send another ray for the next pixel and another ray for the next pixel. So this is a little preview of some of the math that we're going to have to do. We're going to, instead of just specifying a width and height, we're going to specify a width and an aspect ratio and calculate the height based on that. Again, you might want to pause and actually read through all the details in the book. Here you can see the positions of the pixels. The first pixel is not quite at the upper left corner. It's about a half a pixel away in both directions. And then the distance between pixels is this delta u in the horizontal direction and delta v in the vertical direction. And we have these vectors, which we're going to construct vu and vv, which help us sort of locate pixels on the grid. So first thing we're going to do is have a function called ray color, which says given a particular ray, let's calculate what color the pixel should be that corresponds to that ray. And for now, it's not very interesting. It just returns black in all cases. But rather than writing 0, 0, 0, just to make it a little clearer what's happening, I'm going to go ahead and just return black. Black color equals color 0, which is just a shorthand for the vector that's all zeros. And of course, we're going to end up needing white in a minute, so I'll go ahead and do that. Now, in main, we have a bunch of setup stuff to do. So instead of width and height, we're now going to do aspect ratio, 16 by 9 being a pretty common one. Width and image height is the width divided by the aspect ratio. Well, that doesn't work. Width is an integer, aspect ratio is a float, so we will convert this to F64. Obviously, it's not going to happen with these numbers, but if we were ever to pick a very weird aspect ratio or a weird width, we might end up with a height of 0. So just in case that happens, we say image height. If image height is less than 1, then just set it to 1. Otherwise, we'd have no pixels at all. And we'll have to make this mutable to make that work. And we want the image height to be an integer, so we're going to take this whole thing and convert it to a I32. Great. Okay. Then we set up some camera properties. Focal length of 1, viewport height of 2, and the viewport width will be calculated based on the viewport height and this ratio of the image width and height. Okay, now the image width, we want this to be calculated as a floating point. Good. The camera center is just the origin. Whoops, there we go. Okay, and then we need viewport U and viewport V. So these are the vectors that point horizontally across the width of the image and down across the height of the image. Instead of writing this out with the width 0, 0, we can just say viewport width, whoops, viewport width times x, which is just a constant that's shorthand for the vector that is 1 in the x, 0 in the other two directions. And similarly here, this is going to be viewport height times y. And actually it's negative, I believe. Yeah, because it is pointing down from the top of the image. This is viewport V. Okay, and then pixel delta is how much space is there between pixels in the horizontal direction and in the vertical direction. And again, we're going to have to tell the compiler we want floating point division here. Good. Whoops. And this is going to be V and height instead of width and V. Okay. We're almost done with the camera setup. Viewport upper left. So this is the location of the pixel at the very top, or I'm sorry, this is the location of the top corner of our image, which is actually slightly different from the location of the top left pixel. All right, camera center minus, and I'll call this focal length times z. Minus viewport u over 2 minus viewport v over 2. And again, rest makes this right 2.0 because it's a floating point 2, not an integer 2. All right. Now this is the top left pixel, which is basically the same, viewport upper left, but we slide over by just a half a pixel in each direction because we want the exact center of that pixel. it's maybe more precision than you care about if you're just doing this for fun, but we'll follow what the book says. Great. Now we can actually construct the ray right here that's going to go from the camera center out to each pixel, and it's going to be a different ray depending on which pixel we're looking at, which depends on the I and j, where we are in those two loops. So now our pixel color is going to be ray color of R, or actually ref R, and R is going to be a ray that we construct. Kind of doing this part backwards. Oops, there we go. Now, pixel center is, all right, so it's the upper left pixel if I is 0 and j is 0, but if either of them are not 0, we just go over however many pixels and down however many pixels. So plus I times pixel delta u plus j times pixel delta v. And these delta u's and delta v's are vectors. Delta u is a vector pointing horizontally, delta u is a vector pointing down just by the distance of one pixel. And I guess we gotta, whoops, cast again. Gets a little annoying, but that's okay. Great. And then the origin of our ray is always the camera center. And the direction is, well, it's a ray pointing from the camera center to the center of the pixel that we're looking at. So that's just pixel center minus camera center. Okay, so this is not very interesting yet because ray color just always returns black. But we can run it just to make sure it still works. Okay. And then we're going to go in and make the ray color function a little more interesting. So first we're going to get a unit vector based on the direction we're looking. So we're just taking that direction vector and normalizing it to, just scaling it down so that it has a length of 1. And these GLAM vec3 types actually just have a normalize method. Oops. That does exactly that. Then we construct A such that it is a value based on the vertical component of that unit direction, but it'll always be between 0 and 1. So since unit direction is a unit vector, unit direction dot y is always going to be between -1 and 1. So if we add 1 to it, now we have a value that's going to be between 0 and 2. And then if we take half of that, we have a value that's always between 0 and 1. Then we use that to get the color we want. So we do 1 minus A times white, and A times, I'm going to call this color sky blue. I just find this section a little more readable if we use these constants. So sky blue is this color right here. So as A goes from 0 to 1, the amount of sky blue in our color goes from none to fully sky blue. And the amount of white is the opposite. We have no white at all when A is 1, going up to full white. Wait, did I say that backwards? When A is 0, we have full white, and as A goes up to 1, we have no white. So it gives us a nice smooth gradient from blue to white as we go down the image. And you can see here what it's supposed to look like, and we'll run it and make sure ours looks the same. Pretty good. All right. And now, more math. But I'm going to skip over the math for the most part. Basically, we're going to define a sphere as an object that's in our scene, and when we cast a ray out into the scene, we want to know, does that ray intersect with the sphere or not? And since the equation of a sphere is this, with all these squared values, it ends up being solving a quadratic. So if you have a ray whose equation is a plus tb, like we saw a little while ago, and you want to know, does that ray intersect the sphere, what you're really doing is solving a quadratic equation for t. And ultimately, it comes down to this, the quadratic formula, where a, b, and c are defined by this complicated equation here. And then here's the values of them, a, b, c. But basically, it's all here as far as the code, and we can just kind of translate that. So we're going to take a point, which is the center of our sphere. We really only need a reference to the point, but since these types are copyable, I'll just pass it in. It doesn't matter. A radius and a ray, of course. And for now, we're just returning a Boolean. Does it hit or not? We don't need the solution. We just want to know, is there a solution, yes or no? OC is the vector from the origin to the center of the sphere, from the origin of the ray to the center of the sphere. So center minus r dot orig. A is in the glam vectors, dot is actually a method on the vec3s. So we can just do r dot dir dot r dot dir. B is minus 2 times, again, r dot dir dot oc. Oc dot oc minus r squared. And then the discriminant is the chunk of math that goes under the square root. B squared minus 4ac. Again, we got to do 4.0 because we're dealing in floating points. And if that discriminant is greater than 0, 0.0, then we have a hit, otherwise we don't. So now we can make the ray color function much more interesting. We'll keep all this for what to do if there's no hit, but if there is a hit with our sphere, and we'll just hard code here for now the sphere we want, 0, 0, negative 1, radius of 0.5, and the ray is of course whatever ray we passed in. If there is a hit, then we return red. So this is what we should get, just a big red circle. We have no lighting or anything particularly realistic, but it just verifies that our math is correct for the ray tracing determining whether it hit the sphere or not. So of course we got to define red real quick. Kind of looks weird to say color X, but you know what I mean. And there we go. So that is it for part 2.